Welcome. We're going to look at some properties of logarithms as well as change of base formula. If you want to pause the video and write these properties down, feel free to do so. Don't forget that they're in your class Google Drive folder, so you can always refer to them there as well. Let's go through some properties of logarithms. Product rule is if you have a logarithm of a product of two terms, you can space those out and take the logarithm of each term added together. So natural log of u times v can be expanded as natural log of u plus natural log of v. These work also for any other logarithm, common logarithms or log base 5 or 3, some other base. LN is just shorter for me to type, so that's why you see those in these notes. Quotient rule, the logarithm of a quotient can be expanded as logarithm of the numerator minus logarithm of the denominator. Power property, natural log of a term to a power. You can move the power to the front and multiply it times your logarithm. I went ahead and inked in a fourth specifically for problems below. E to the natural log of x equals natural log of e to the x equals x. What this property says is if your base and your logarithm have the same base, like natural log is log base e. Well, if you have e to a natural log, those will cancel each other and leave x. Same thing here. Again, natural log is log base e. This term has a base e. If those match, they'll cancel, leaving x. The shortcut that I gave you in class was if you can get e and natural log to touch, no matter the order, they will cancel one another, and that's true. Also, logarithms of various bases like 3, 5, or 7, I'm just making up numbers, those can be simplified using common logs or natural logs in what's called a change of base formula. Here's an example. Log base 3 of 77. Ultimately, what we're looking for with this expression is what power of 3 will equal 77. Well, there's not an exact power. 3 cubed is 27. 3 to the fourth power is 81. So we never hit this actual number of 77. That doesn't mean we can't get the value. If you use a common log, it's going to be log of 77 divided by log of 3. If you use a natural log of 77 over natural log of 3. It doesn't matter which logarithm button you press on your calculator, as long as it's the same one both times. This is the approximate power of 3 that will get you to 77. Okay, let's look at solving some exponential equations. First example, we're going to solve 3 times e to the x equals 35. And what we're going to do is we're going to isolate the exponential term. So divide both sides by 3. E to the x will be equal to 35 over 3. To solve for x, we need to eliminate this base e. Natural log, back up here at property 4, if we natural log both sides of the equation, natural log and e will cancel each other out to get x. Natural log of 35 over 3, this is your exact answer. WebAssign may want you to approximate. Just type this in your calculator, press natural log, 35 divided by 3, close that up in parentheses, and you can check this answer. And we did in class, we took this answer and we multiplied 3e to the answer we got, and we got 35 back. If you use a rounded off number, when you check, you'll get approximately 35. The middle equation, e to the x minus 2 equals 37. Let's isolate the exponential term, add 2 to both sides, e to the x equals 39. Solving for x, we take the natural log of both sides. X will equal natural log of 39. This is your exact answer. If you put it into a calculator, round to 4 decimal places, this is your approximate answer. If you substitute this back in the original problem, depending on how many decimal places you keep, you will either get 37 or real close to 37. Our final example, 5 to the x plus 8 equals 28. Let's isolate our exponential term. Subtract 8 on both sides. 5 to the x equals 20. Now note, this time our base number is not e. That's okay. We can get around that using change of base formula. So we have a base number of 5. If we solve for x, we could take either log of 20 divided by log of 5. I just use natural log of 20 over natural log of 5. This is your exact answer, and it's approximately 1.8614. If you substitute that back in, check it, you'll get 28 or real close to 28, depending on how many decimal places you save. Solve each logarithmic equation. In our first example, we have 2 plus 8 times the natural log of x equals 5. Let's isolate natural log of x. Subtract 2 on both sides. 8 natural log of x equals 3. Divide by 8. Natural log of x equals 3/8. Now, in order to eliminate natural log, we exponentiate both sides with an e. Natural log is log base e, so we will exponentiate with that base number e. If you get e and ln to touch, they'll cancel, so x is equal to e to the 3/8 power. This is your exact solution. Putting that in a calculator, 1.4550 is the approximate solution. One thing about logarithmic equations is you have to make sure that the answer you get at the end doesn't create 0 or a negative in your logarithmic term, and this one doesn't. In our next example, natural log of x plus 2 minus natural log of x minus 4 equals natural log of x. We can't use the one-to-one property because we have 2 logarithmic terms over here. Now, let's pay attention. Between these 2 logs, there's a minus sign. I'm going to scroll back up. Property 2, the one that's highlighted, tells us that if we have 2 natural logs or any logarithms that are subtracted, we can condense that down to 1 logarithm if we make a quotient or a fraction out of their terms. So let's go back down. These 2 logarithm terms can be written as 1 natural log, but we have to write it as x plus 2 over x minus 4. Now we have natural logs on both sides. You can use the one-to-one property, and that says x plus 2 over x minus 4 has to equal x, or you have the option of exponentiating both sides with a base of e. Either way gets the same job done. Starting here, solving for x, let's multiply by the denominator. X plus 2 equals x times x minus 4. That's x squared minus 4x. Because of the quadratic term, I've subtracted an x and I subtract a 2. That gives us 0 equals x squared minus 5x plus 2. This won't factor with whole numbers, but we have a backup plan. We could use quadratic formula. Negative b, that's 5, plus or minus the square root of b squared minus 4 times a times c, 25 minus 4 times 1 times negative 2. That gives us a discriminant of 33. over 2a, 2 times 1 is 2. Using the plus sign, 5 plus square root of 33, all divided by 2, gives us an approximate answer of 5.3723. Using the minus sign gives us an approximate answer of negative 0.3723. Now let's remember those two values. Back up here in the original problem, 5, and I'm just going to make it real short, 5.4. 5.4 plus 2 is positive. 5.4 minus 4 is positive. 5.4 is positive. This top answer we get to keep. When you try to use the bottom answer, you're okay with this first logarithm, negative 0.37 plus 2 is positive. But right here and right here, all you have to do is violate one domain, and you got to throw the answer away. This one here fails. If you plug in our negative 0.3723, subtract 4, immediately negative, and that's why I crossed this answer out. So you've got to watch out for domain violations. Let's solve this last logarithmic equation. Log of 2x plus 3 equals log of x minus 8. This will fall into a problem where we can use a one-to-one property. You could also exponentiate with a 10. You could put 10 as the base on each side of the equation. 10 and log are inverses, so they'll cancel. Just like e and ln, 10 and log will cancel each other. But let's use one-to-one property. 2x plus 3 equals x minus 8. Subtract an x, subtract a 3, and we end up finding that x equals negative 11. The problem is negative 11 creates negatives in your logarithmic terms in the original problem. And since there's only one candidate, but it fails, there's no solution to this equation. In class, I graphed each side of the equation as separate graphs, and those graphs never did intersect.